Thank you so much, Pablo. So good morning, everybody. It's a real pleasure to be here. And I first need to thank the organizers for giving me the opportunity to tell you a little bit about my recent research. So over the years, I studied completely different systems. So I'm a rheologist, an experimentalist. I dealt with systems that go from colloidal polymers to polymer melts. And then a few years ago, I accepted the challenge of studying Coacervates. So I think you can convene with me that most of the people studying Coacervates are inspired by nature, and so I was. So what really intrigued me at some point while reading paper is the ability of the so-called sandcastle worm to basically gather sand grains, produce a certain glue, and they are able to really build very big structures where basically they live and proliferate. So it's a special glue, so that is also very resistant underwater, and therefore, as a material scientist, we are always intrigued and say, okay, so can we understand these materials? I found a paper explaining a little bit what's the physics and chemistry behind this secretion of sandcastle worm, and I found that at the end of the day, what happens is a complex coacervation. So the sandcastle worm secrete this biological glue, which is basically made of charged proteins and ions. So we have phosphorine and lysine, which in the presence of some amino acids, it's they are able to make this complex coacervates. So meaning that there is a phase rich in polymer and a supernatant, so a phase that is basically rich in the excess ions. So from a rheological point of view, having a complex coacervates give us a very wide plethora of opportunities to tailor rheology. So here is just a simplified version of, let's say, properties between a simple polymer solutions and a complex coacervates. So in both cases, you can have entanglements. So in both cases, you can have a temperature responsive system. So you can tailor, for instance, the solvency conditions in polymer solutions. But when we talk about pH responsive, when we talk about salt responsive and gel-like response, so complex coacervates, in a nutshell, can really prevail simple and neutral polymer solutions. So that's why we are intrigued in these systems. So before going forward, I would like to have everybody on the same page. So I need to just give a little bit of information about the so-called small amplitude oscillatory shear. So all the experiments provided in these presentations are just shear rheology during oscillation. So we have our systems, which is basically sandwiched between two plates, and our rheometer applies a sinusoidal shear deformation into it. And through a transducer system, we are able to get the output, the response, which is a stress that has the same sinusoidal shape, but there is also a phase lag here, or phase shift. So now, if this phase shift is basically zero, so input and output are in phase, and we are describing an elastic solid. So if this delta is basically 90 degrees, we are describing a viscous fluid, so we have a cosinus response. And it goes without saying that between 0 and 90 degrees, we have a viscoelastic materials. So we can use basically rheology, looking at the phase shift and understand whether the material is more solid-like or liquid-like. So once we know the response, there is a set of rheological functions that we can get. So we have the stress that can be basically split into two contributions. I think many of you know the G prime or storage modulus. So this describes the elastic contribution to the overall response. Then we have G double prime, which is the viscous contribution to the response. And then we can also have the complex modulus, which is basically the the average of the square of G prime and G double prime. Then we have the tan delta, which is the loss factor, and eventually the complex viscosity, which is just the ratio between G star and the frequency that we are looking at. So this is just to tell you that when we measure rheology, we have access to all these rheological functions, and they always help us to understand whether material has entanglements, is more liquid-like, is a Newtonian liquid, and so forth. So this is really a rheology explained in a very simplified version. But what I would like you to notice is that there is a very powerful way of plotting rheological data, which is basically the phase shift, so between 0 and 90 degrees, so how solid or viscous-like is the system, against the complex modulus, okay? So this is a typical frequency-independent plot, and it goes under the name of Fancourt-Palman plots. So after these two guys here that developed this representation in 1998, and basically with this representation, so we are able to test and assess superposition principles in coacervates, but not only. Actually, for the first time, this was used for the so-called time-temperature superposition principle, because you can put the raw data in this representation, so you don't have any shifts in the time domain. Therefore, if the data collapse, the time-temperature superposition works, and if it doesn't collapse, then the superposition doesn't work. And eventually, over the years, this can be applied to pH-responsive systems, salt-dependent system, and so forth. So superposition principle. So now I'm going to give you a little bit of state of the art on biopolymer-based coacervates. So here we have chitosan and hyaluronic acid. So in this case, in this study, so we have observed that just by changing the pH of the system, you can basically tailor a system from a liquid-like behavior where the G double prime, the viscous modulus, overcomes the elastic contribution G prime. And when we increase the pH up to 6, then you see that there is a sort of gelation or arrested state or arrested dynamics, the way we prefer. So the thing here is that as soon as you increase the pH, all the protonated amine that we have in our chitosan, they are not protonized anymore, and therefore they can give birth to hydrogen bonds, intramolecular bonds with other chitosan chains, or with hydrogen bonds with the hyaluronic acid, hydroxyl and carboxyl groups. So another contribution is certainly coming from Sarah Perry's group. So she has been working on coacervates for a very long time. And she also demonstrated that if you complex coacervate chitosan and hyaluronic acid with alcohols, you can tailor the interactions between the two coacervates. And therefore, if you also electrospin fibers, you can also vary and tailor the homogeneity and uniformity of such fibers. So recently, we also played with similar systems, but in this case, the polyanion was synthetic. We could also modify the degree of hydrophobicity via the protection mechanism. So meaning that if this sulfur groups is deprotected, so there is no isobutyl groups here, so it becomes a very simple coacervate, whereas if this is like the isobutyl group is present, we have a protected system, so we can only have hydrophobic interactions. So again, so we can tailor the electrostatic interactions of the polyanion via hydrophobicity degree. So whereas the polycation is just taken as such. And we have also made underwater adhesives by using these complex coacervates. So long story short, when we looked at the rheological data, we were able to generate master curves using a time salt superposition principle, but also time hydrophobicity superposition principle. And just by using the Van Coor-Palmen plots, we see that all the data, so this is as a function of salt, and here horizontally is as a function of the protection degrees, or if you want the hydrophobicity degree. So we were able to basically have a very nice overlap of the data naturally. So this kind of superposition works. You can also use the same coacervate to 3D print directly underwater. So basically obtaining objects so that they can keep the shape even for 3 months. So this was at the beginning. This was basically after 3 months. So not so bad. And certainly these are not the most important works, but there is a lot out there. So I need to certainly acknowledge the review by Larsson that we have here, superpositions in polyelectrolyte coacervates, or another beautiful review from Sarah Perry's group. But interestingly, even Rubinstein now is working on scaling theory for symmetric and asymmetric coacervates. So there are very interesting things out there. So rheology-wise, what I identified is that the asymmetry in molecular weight and the effect of this asymmetry in molecular weights and also asymmetry in charge on the relaxation dynamics is kind of lacking. So I said, okay, I would like to contribute to this topic. And that's why I also chose this, let's say, natural biopolymer complex coacervates. And for these studies, we made basically 9 systems. So we have 3 symmetric coacervates, and in this case, the symmetry is in molecular weight, or at least a range between 30K and 30 and 50 kilograms per mole, and 6 asymmetric coacervates. So we vary only 1 molecular weight at time. So that's all the pairs that we have analyzed. So something important to stress is that charges are always neutralized. Okay, so there is no excess charge in these systems. It was not in our interest to vary the asymmetry in charge for the time being. So I think the first thing to do is basically the phase diagram, and to check when you can basically generate a complex coacervates as a function of salt. So we have done that via light transmittance, and well, I also put here just a picture to show that at some point, as you increase salt, you have screening charges, and you cannot obtain a complex coacervate anymore. So just to start with some rheological data for the symmetric, let's say, pairs. So we have in red low molecular weight. So if you want, you can consider it unentangled. Okay, so that we can see that there is also the onset of a Newtonian plateau. So it means that this system obtains full relaxation. Whereas for the medium and high molecular weight pairs, we have just a shear thinning, let's say, behavior. So this is more like an arrested state within the probed frequency range. So jet-like response. As you increase salt, however, you see that the viscosity lowers in magnitudes, and the system becomes weaker and weaker, as expected, nothing new. So you add salt, you screen charges, so the polymer chains, they become more Gaussian-like, so therefore the mobility increases. Then we look at the unentangled system, so the lowest molecular weight that we let's say probed, and then we observe that the time salt superposition principle holds up to a certain salt concentration. So we could see from the so-called Van Coor-Palmen plots that up to 0.4 molar of salt, so that we added in our system, everything works perfectly. But then at some point when you reach this critical salt concentration, then the time salt superposition vanishes. So that's also something to think about. That's how the master curve would look like. And if you see, if we also start adding at 0.4 and 0.5, then there is a slow mode here that, as a matter of fact, is an artifact. So when we move to an unentangled system, so high molecular weight, so these are still viscosity values, but when we do the same exercise with high molecular weight, so entangled system, it looks like that the time salt superposition cannot be applied, not even at very low salt concentrations. So this, to some extent, is not surprising because now we have relaxation modes that are salt sensitive, but we also have relaxation modes such as reptation, constraint release, chain fluctuations, and other relaxation modes that they do not really couple with salt the same way. So that's basically one of our findings. So entangled system, at least for this biopolymer coacervates, so the time salt superposition vanishes with salts. So then we started collecting the relaxation time of these coacervates for symmetric pair and asymmetric pairs. And here we witness, let's say, two important things. So there is always a two regime that we see in the relaxation time. So there is a regime where the salts doesn't really change much the relaxation time, but after a certain critical concentration, there is an abrupt, let's say, a drop in relaxation time. And it seems that this drop is more pronounced every time the molecular weight of the hyaluronic acid is high, or certainly higher than the molecular weight of chitosan. So this is also something that we are able to see better when we look at the asymmetric pairs. Like, for instance, you see these open red triangles, okay? So where we see that we have low chitosan and high molecular weight of hyaluronic acid. And you see that the dependence of the relaxation time on salt is very weak. So this means that the relaxation dynamics is, as a matter of fact, controlled by the hyaluronic acid. And not because the hyaluronic acid is the polyanion, but simply because the hyaluronic acid is the stiffest chain in the system. So if we look at the Plato modulus, we witness something similar. So first regime where salt does not really play a very big role. And then at some point you had a very abrupt decrease. And again, every time the hyaluronic acid has a high molecular weight, so you see that the drop is always weaker. So this seems to go pretty well with the recent predictions of Michael on complex coacervates. But as a matter of fact, we had to find a sort of physics and rationale behind this. That's what we are thinking at the moment. So if we look at the persistent length, we are talking about hyaluronic acid for 10 nanometers. So the chitosan is relatively lower, so 1-4 nanometers. So indeed, the hyaluronic acid is much stiffer compared to chitosan. So this means that it undergoes a slower disentanglement dynamic and, of course, chain retraction. And these modes are usually not very sensitive to ionic screening. Also, I found that when you deal with the hyaluronic acid, so it's much more hydrated than the chitosan. And some people also discuss about structured water layers around the hyaluronic acid chains. So this also makes the dynamics much slower. In order to check also the adhesive properties and how we can basically tailor the adhesive properties of complex coacervates, we perform the usual TAC test. So you basically have your coacervate between two plates. This can also be done in a rotational rheometer, and then you lift the stage at a constant speed, and then you measure force as a function of the formation. So you can get the stress-strain curve, and if you make the integral of these curves, you can get the so-called adhesion energy. Okay, so that's in a nutshell what we have performed. You can already see that the adhesive energy for asymmetric system is much more pronounced, and even the maximum peak is much higher compared to the asymmetric pairs. But what we have observed is the following. So if we want to, let's say, design adhesives, especially that they also work underwater, so if we are working under low salt concentration, then it's better to have a symmetric pair, or you need to have a molecular weight of hyaluronic acid, which is lower than the chitosan. Or if you are working at high salt concentration, it's better to have a high molecular weight symmetric, or you need to have the asymmetry on the other way around. So where the molecular weight of hyaluronic acid is larger than chitosan. So you see that there are so many parameters one can play with, and depending on the operating conditions, one can design complex coacervates with superior properties just by playing with asymmetries. So just to conclude, I would like to highlight these three main messages. So molecular weight and chain stiffness control self-dependence. So I remember in the past, there was always this debate between what controls what. Is it the polycation? Is it the polyanion? I think that chain stiffness plays also a very important role, maybe even more. So time salt superposition is valid only for unentangled systems, at least for these complex or biocomplex coacervates, let's say. And of course, next thing to do is to look at the asymmetries in charges. So that's also something that Michael has been developing some scaling theory. So it would be nice to experimentally test them. So with this, I cannot refrain from thanking the student who performed all the experimental work, and a very close collaborator of mine, Marlene Kamperman, also at the University of Groningen, and of course you for your attention.